Okay, welcome to class meeting 7 of EECE574, the graduate level probability and random processes. First, we have announcements. Quiz 1 is going to be taken on this Thursday during the class meeting hour. It will take up 1 hour, 15 minutes, and it covers up to today's material. And it takes up 10% of total 100 of your course requirements. As I emphasized, you can use anything except any assistance from a human being. You will be given paper printed problems, and also you will be given a blank booklet, answer booklet. So you will use answer booklet and just turn in to the TA. Homework 4 will be due on next Tuesday and assigned by the end of this Friday. Handout for class chapter 4 is updated. So if you have downloaded last week, please update it, reload it again. Passwords are, as you know, 4, 5, 6 in lowercase English alphabets. Recorded class meetings and annotated PDFs are continuously uploaded to the CISL Postec homepage and also YouTube channels. There have been several messages from me. Simplify and visualize must be your doctrine too. And also I want to emphasize that one of the methods to simplify is not just reduce the size, but divide it into several sub-problems. And then for each sub-problem, you may apply that simplify idea by keeping some or all of the essence of the sub-problems so that you simplify until you can solve it. And then you take the reverse to get the entire problem. And you integrate those sub-problems to solve the original problem. So it's like not just divide and conquer. That sounds like very harsh. Divide, conquer, and integrate, harmonize, something like that. I also emphasize the importance of these lessons from great inventions. And I also want to tell you that since most of you are starting graduate students, you have to distinguish these two value system in your brain. So far, some of you may have this stage clear idea in almost every stage of your life. For example, you enter the university, then you cleared one stage, you got a high GPA in a specific course, you cleared the stage, you got a bachelor's degree, you cleared the stage. That does not hold, or that shouldn't be hold as your value system if you become a graduate student, because it's no longer clear staging system. You must improve yourself every day. It's not like, okay, somebody acknowledges that you reached that. That is not enough, because without improving your skill, your knowledge, your thinking capability, it's not easy to have a good thesis, good theoretical results after your years in the graduate school. So please modify that idea to growth-oriented or improvement-oriented, or in Japanese business term, kaizen, in Korean 개선, kaizen type value system you must have. Okay, here goes the overview. We are still working on the third part, especially this expectation part of chapter 3 of our undergraduate textbook. I hope we can finish this chapter 3 today and move on to chapter 4 with multiple random variables. Okay, Any corrections and clarifications? It seems none. So last time we worked with expectation, and one of the key results was this one. So suppose you have an underlying probability space with sample space, event space, and probability measure P, and you define a measurable function with domain, the sample space, and the range, the extended real line or the real line. Then you can define the expectation of the indicator function of x with some event A, and this event A may be event A may be the event space. May be an event in the original event space, or you may choose A as an interval-like subset that is a Borel set. Okay. Then, interestingly, we can link the expectation with the probability. So in the upper case, we may write it like this. Let me see. Yeah, not good. Okay, let me just use the second one. So A is a Borel set. In that case, you have to write this way. Okay, so you use the induced probability space, and that measures the size of the Borel set A. Okay, something like that. So you can link the expectation and probability by using the indicator function. The important application, one of the important application was the proof of inclusion and exclusion principle. So I asked you to specifically do that. Then we moved on to the conditional expectation, something like this. So we have expectation of a random variable x conditioned on the occurrence of the event A. And also, I said that we can use the indicator function to simplify the notation. There goes the theorem, also using the conditional expectation. So we want to compute the expected value of a random variable x by introducing a partition. We may have something like expectation of x given a sub I and probability a sub I, something like that. Okay, so the expected value is what? Is the summation of the product. Then suddenly your sum of the neurons must ring the bell. Anyway, value times probability. What does that mean? It's expectation, right? It's an expected value. Value times probability is always the expected value. So it's like this is the total expectation, we say, and this is the conditional expectation. So we can verbally say that the total expectation is the average or expectation average of the conditional expectations. And what's the physical implication of that? Whenever you are given an object, in order to find the center of mass, right? You compute something similar to the expectation of a random variable. And then this theorem has a counterpart in physics saying that you divide the object and find the center of mass of each part and represent each part using a point mass with the mass corresponding to each part And then if you compute the center of mass of the systems of point masses, then it becomes the center of mass of the original object. This is exactly equivalent to that idea. So yeah, this is total expectation. And what is the fundamental theorem of expectation? It's like this. Suppose you have a deterministic function, g, and your input is now x. Then what happens? As you learned in your high school probability and random processes, because the output is a real number with uncertainty, and input is the real number with uncertainty, modeled as a random variable, we also model the output as a random variable. That's obvious. The question is related to expectation. So given that, what is the expectation of y? What is the expected value of the output random variable y? And our straightforward approach to this problem is to derive the CDF of the new random variable y and apply our definition. However, the fundamental theorem says that you can write something like this. Of course, g of capital X is our new notation that denotes the random variable y. So this is just the replacement of a symbol with a notation. But here goes the interesting part. What? We find that this. So actually, you can even say that this is defined as that one. Okay? However, the theorem says that this is a notation and this expectation is same as that notation. So in your probably undergraduate course, this was defined as that one. However, what I'm saying is that this is shown to be equal to that one. That is the theorem for the fundamental theorem of expectation. So the situation is very similar as I once told you. In your high school, the fundamental theorem of calculus was given as if it was a definition. Actually, it is a theorem to be proved. And that proof was usually delayed until your undergraduate calculus course. About moments. So here, G function, deterministic function, is now a very interesting family of functions. So it's a power function. And in Korean, or not Korean, how to say that? The 한자어, 멱급수 or 멱함수. So you have a power of the input. So if input is x, then output is x raised to the power of n. By the way, how do you read this? X raised to the power of n. Okay. So this is the full reading of that x to the n. But why we simply say x to the n? X to the power of n, and sometimes x to the n. Okay. So anyway, so this is a special case of general fundamental theorem of expectation. So instead of computing the PDF of the random variable x to the n, we apply the fundamental theorem to find something like this. Here, the theorem tells us how to compute this expectation. See that? We identify something random. For example, if we identify something random as this g of x, entire g of x, then this expectation becomes what? This expectation becomes integration of a dummy variable y and the PDF of y of dummy variable, the dummy variable. Okay? See that? So if we view this entire y as a random quantity, we need density of y. If we view this x as random quantity, then we use density of x. And you have to introduce a dummy variable, x or y or z or k, anything. But anyway, your integrand not only has the density of x, but also has g of x, g of dummy variable. Got it? So similarly, here you've done what? You identify x is the random quantity. So you use the PDF of x and you replace capital X to a dummy variable raised to the power of n. In this case, we choose usually x because this is x, but you can choose y or z for the dummy variable. Okay. Anyway, so this is our kind of way to compute the moment. However, here n must be what? So far, n is assumed to be integer. And our convention is that in case of n equals 0, we usually, or almost every time, we say that this is 1 and 1. Okay? Unless x is a degenerate random variable that equals 0 always, something like that. Anyway, so most of the times. But anyway, we are interested in the case that n is an integer. The problem is that even when n is 1, this existence of this expected value is not guaranteed. And what was the representative example? The Cauchy distribution with 1 over pi times 1 plus x squared in the denominator. So it has much heavier tail than, for example, Gaussian density, so that you have a problem if you multiply x and integrate. Okay. Anyway, this type of thing is called the non-central moment. And if we subtract the mean, then these types of moments are called central moments. And sometimes we use the absolute value instead of simple parentheses. In that case, these are called absolute central moments or absolute non-central moments of x, something like that. Now that we have defined and talked about the existence of the moments, let's derive some results. By the way, due to the definition of integration, which involves the limit operation, usually whenever you say limit is unique if it exists. So we rarely talk about the uniqueness part. We mostly talk about existence part only. Some of the definitions of the mathematical entity involves a limit operation, and by definition, limit is unique if it exists. Right? Anyway, so let's see this one. So we want to find non-central moments, which means that expectation of x to the n. By the way, what is this one? A non-negative random variable. So here goes the definition of a non-negative random variable x. That is very simple. Probability of the event that x takes non-negative value with probability 1. Okay, so this is called with probability 1. This is not just my notation. people use that. Mathematicians, statisticians, electrical engineers, they use that. W dot P dot 1 with probability 1. Got it? Sometimes it is called almost surely. Which is abbreviated to A dot S dot. Okay, almost sure. So X is almost surely non-negative, which means that X is a non-negative random variable. In the probability theory, we are not saying that definitely something. If the probability of that event equals 1, then we say that it's almost surely something. Got it? Now, the question is that given a non-negative random variable X, does non-central moment has something special? Yes, that's why I'm talking about this. And in your undergraduate course, some of the textbooks have shown this expression and you are puzzled. So let's see. This is expected value of the nth order non-central moment, right? And here we have non-negativity. That's why in this integral that involves the value of x, right? The lower limit is 0 and upper limit is infinity. Got it? Now, you have something you can easily notice that looks like derivative of x to the n, but it is not. So it is. So what is the unit of this part of this factor of the integrand? The unit of x raised to the power of n minus 1. Now, what is the unit of this part? The probability has no unit. Or if you rely on the frequency interpretation, it's total number of trials and the number of occurrences, which means that it's a unitless quantity. What is the unit of dx? In our math course, we rarely talk about that, but in our physics course, it's very important because dx has the same unit as x, because this is simply difference between x sub I plus 1 and x sub I. Both have the same unit as our x. So as you see, the integrand times this dx has the unit same as x to the n. Got it? So never make a mistake like writing this part as x to the n. If you multiply x to the n with dx, unit does not match. This trick is usually called by physics students unit trick. Okay, so whenever, well, for example, you are given a multiple choice problem, it's like, okay, you have a glass plate and this side has temperature T1, that side temperature T2, conductivity is something, the width is something, area is something, 1, 2, 3, 4. Which one is the correct heat transfer per second, something like that? They just check the units first and remove the absurd choices with unit matching technique. Okay, so anyway, as an electrical engineer, you must be also good at that. Okay, never forget. Anyway, so this is something strange. I'm not going to talk about this. I will defer it to your homework, or you've already done in your homework. What I'm going to show is the special case. So I'm going to simplify this one to the case with n equals 1. So I'm going to show you why this is true or why this looks true. So e to the x, and we assume x is almost surely non-negative. Okay? So here goes the visualization. Okay, so I simplified to n equals 1 case and visualize by drawing something. So let's start from our status integral form of the expectation. So what's that? This status integral form of expectation is really motivated by this one. Expected value is simply the sum of the products of the value times probability. Got it? So this is kind of rewriting of that one, right? So sum becomes integration, x sub I becomes x, difference between two CDF becomes d CDF. Now what we do is that we draw the curve over CDF of random variable and see what does this mean. Okay, so here goes the CDF of a random variable x. I haven't yet assumed it's non-negative. Not yet. Non-negative random variable. Okay, so our CDF is a monotonically increasing function, possibly discontinuous, right? And bounded by 1 and 0. I just draw something similar to the Gaussian CDF. Now, let's take a look at what does this mean. Okay? And if we use our Riemann integral approach, right? It's like, okay, we have x, and I don't know. But usually, when we have this Stieltjes integral form, we are forced to rotate the axis and apply the Riemann integral type thing. As I told you, Stieltjes integral itself can be combined with Riemann integral and also with Lebesgue integral. So anyway, whenever you see something like this, first draw this cumulative something and then rotate the axis, and it's easy. So let's see. For each value of x, right, you have this one. Now you rotate that, and this is important. So you divide this y vertical axis and then find what? Find in this slice, what is that? This is the value of x sub I in the ith slot or bin, right? This is xi, and the value here, how do you say that? Yeah. This height is simply xi plus 1 minus fxi, right? So I'm computing this product. And this product corresponds to the area of this rectangle with wide side, right? So this corresponds to that summand. By the way, I use the term summand, integrand. What are they? When you have sigma notation to sum something, this part is called summand. When you have an integral form, then this is usually called integrand. Some small group of people call the entire thing as integrand. But I would say that this is summand because this corresponds to the entire one. Got it? Anyway, so according to our Stieltjes integral form of the expectation, each at the ith summand, ith product corresponds to this area. Now, let's think about the case where x is positive only. So you start from that one and this area, you increase xxx, then you cover what? You suddenly have an idea that if x is greater than or equal to 0, you are expecting that part of your expectation. So if you divide this integral from negative infinity to 0 and 0 to infinity, the second term is the area of this part. Now, what about the negative part? So let's consider some negative value, x sub I. And then you again has what? This value and that value. Since here goes the important part. Whatever the sign of x, whether it is plus, positive, or negative, this dfx x is positive because we divide x from, and we divide this x interval, for example, and then the bin in the x has increasing order, right? And the CDF is, as I told you, always increasing. So bin in the y-axis also has the increasing order. Got it? So this part is always non-negative because it's probability. So anyway, here, this corresponds to dfx. Now, what is this one? This is simply that area. And you have to multiply what? Minus. Okay. See that? This x of I is negative now, right? So if you multiply this value times that, your second part, right? So let me divide into your first part, actually. So we've done that one. So it's 0 to infinity, 1 minus fx dx. And this part is what? The area of this one times negative sign. So you compute the area and must subtract. So negative 0 to infinity to 0 x dx. So here I find this is wrong. Okay, you have to put negative sign. Got it? You need negative. So interestingly, if we use the Stieltjes integral form of expectation, the expected value of a random variable is not yet non-negative, can be divided into two parts, one area and the other area, subtractive, right? Now, if we have non-negativity of the random variable, then what do we have? We don't have this term. So what is the definition of CDF? Capital X greater than or equal to X. 1 minus probability is the probability of its complement. So probability of the event that capital X less than X. Got it? Sorry, greater than X. That's here. So we have this strange looking form. And you do the same thing for the x to the n, and you get that result. By the way, show this was the qualifying exam problem when I was taking the QE, when I was a graduate student. So do it, okay? Now, as written here, sometimes we use multiple representative values to partially characterize our random variable. As I told you, a representative value of a multiset never fully represents the multiset. Also, similarly, no representative value, possibly no moment, no central absolute, non-absolute, does not, in general, fully characterize the random variable. So just the mean is not enough. So we sometimes put the standard deviation, or sometimes the variance, or even we put sometimes higher order moments. And here goes some higher order moments. But before I talk the higher order moments, let me emphasize this one. So this auxiliary, in Korean 보조, auxiliary representative values may have different units than from the original random variable. For example, here, suppose x is a random variable, has unit meters. Then what is the unit of the variance? Meter squared. Got it? But standard deviation has the same unit. This does not look very important yet, but you will someday find that's very, very important. By the way, when we compute the moments, sometimes we standardize and then compute the moments. Here, by standardization, I mean is that we find so-called z-score. So we have some linear transformation like this. So we subtract the mean of x. So let me use subscript capital X so that this mu and sigma is the mu and sigma, the mean and standard deviation of the random variable x. Now, what is the important question is, what is the unit of z after standardization? It does not have unit. It's a unitless quantity because the numerator and the denominator have the same unit. Be careful, the numerator has two terms and both have the same unit. As I told you, any arithmetic sum or so addition and subtraction requires two physical quantity to have the same unit. Got it? Anyway, so this is a unitless quantity. And you will see that in order to standardize, you must have the mean exists and standard deviation exists. So once you have very special first order moment and second order moment of random variable exist, and then you standardize the random variable and, for example, find so-called the skewness and the kurtosis of a random variable. These are standardized higher order moments. So what is skewness? Very simple. Here, n equals 3. Okay. By the way, after standardization, if the exponent is 1, your value is 0 because you subtracted the mean. Expectation of z equals 0. Expectation of z squared is 1. Got it? Expectation of z cubed, then what happens? It could be positive, negative, or 0. But why this is called skewness? We usually compare our centralized and also standardized moments with those of the Gaussian random variable. And as you know, the Gaussian random variables are fully characterized its mean value and the variance. And what do we have? As I wrote here, especially the standard Gaussian has some interesting results. Mean is 0, variance is 1. Any odd power moment is 0. Any even powered moment has something special. Probably you've seen something like that. The fourth order moment equals 3 times sigma raised to the power of 4. And what about z to the 6th? 1, 3, 5 times sigma raised to the power 6. And I myself, when I was at your age, had difficulty in memorizing that. And sometimes I got confused, so I had to not Google it, because at that time Google was not yet launched. But anyway, one way to remember is this one. Anyway, you standardize. So your mean means nothing, right? So in this case, by the way, let me write this way. I just use centralize only. So let me change this to, yeah. No, not that. It's confusing. Okay, so Okay, let me keep that. Then let me take this sigma out. Okay, so far. So you have other numbers here. And if this is 2 to the n even, then you multiply 1, 3, 5 up to, 2n minus 1. So z to the 2n, expected value equals 1, 3, 5, 7 up to 2n minus 1. Now, if you do not standardize but just centralize, let's see what happens. Expected value of y to the 1 is 0, similar, right? Because you centralized. Y square is sigma square. Y cube is 0. Y raised to the power 4 is 1, 3, and sigma 4. Y to the 2n equals 1, 3, 2n minus 1, sigma 2n. And how I'm sure? See that y has the same unit as x. Sigma has the same unit as x. See that? The exponents must be the same. Otherwise, it does not make sense. Got it? So y to the 2n, sigma to the 2n. Got it? Anyway, so Gaussian random variable has something interesting. And Gaussian density has perfect symmetry with respect to its mean. So after we centralize and especially standardize, we check the third order standardized moment. And if it is positive, we say that it's skewed to the positive part. If it is negative, it is skewed to the negative part. So this skewness over random variable gives us a rough idea of asymmetry. Got it? It does not say that the skewness 1 compared to 2 is more skewed than skewness 3 compared to 2. It does not say anything. However, it just gives us a rough idea. If its value is very, very small, then it's almost symmetric. Now, what is kurtosis? There are two types of the kurtosis. First one is simply the standardized value, z squared raised to the power of 4. Okay. If Gaussian, what's the value? As I told you, it must be 3. Okay. So some people subtract 3 from this quantity and then check whether it's positive or negative or equal. Some people compute that and compare with 3, whether it's greater than 3, less than 3, or equal to 3. So there are two types of kurtosis. But anyway, it's a measure of tailedness because see that you compute the fourth order polynomial. So you have very fast growing thing. So if you have a large probability here in a big value of x, then what? This kurtosis becomes large. So tail probability is very important. As I told you, Gaussian distribution is so-called a light tail probability because its PDF has what? E to the negative x squared. So it has a very light tail. It's exponentially, and the exponent is even quadratic, so very fast. However, for example, as you've seen in the Cauchy distribution, the tail is what? Reducing. However, it's inverse quadratically reducing. And as you know, that the even if you claim mean is 0, variance does not exist. Because see that x squared times 1 over pi, 1 over 1 plus x squared, that does not converge at all, right? Got it? And if it is raised to the power of 4, it blows up, right? So this kurtosis is a kind of, see that? Not the, it's a measure of tailedness. It's just a convenience metric. Now, you've seen the function called the moment generating function of a random variable. And this moment generating function is defined by using the expectation. So it's like this. You have a random variable x, and you compute what? E to the new x, and take the expectation. Got it? First, let's see what is e to the new x. Yeah, it's an exponential function with some parameter nu, and usually its value is taken as a real number. However, you can use complex number. So it's like this. Suppose you have x, and you have e to the nu times something. So you have e to the nu x. If nu is real number and positive, what happens? Your graph looks like that, right? In your side. If nu is negative, it's decaying to 0. Now, instead of using the variable x, we use random variable x. And our notation says that output is denoted by e to the new x, which is a new random variable. Now, the moment generating function is defined as the expected value of e to the new x. Now, here goes my question. What is this one? It's a real value if nu is real, right? However, if you change nu, this real value may change. So we usually say that this is what? A function of nu. Got it? Function of the variable nu. So definitely this is a function, is a function of nu. Let's say that nu is real. So this strange thing can be, for example, denoted by capital M sub capital X sub nu, because it's a function of nu, right? Now, what is M? Because we are going to claim that it can generate moments of random variables. So moments starts with M, so we use capital M. And given random variable X, it may have moment generating function. Given a random variable Y, it may have random moment generating function. So subscript means it's the moment generating function of the random variable X, parameterized by nu. Now, let's find the integral form of this one. According to our fundamental theorem of expectation, what? You can put everything together as a random quantity, or simply X as random quantity. We take the latter view, and we may have this result. Got it? Am I right? So we have e to the new x PDF of dx, PDF dx. And some of our neurons say that, yes, it looks very familiar. And here goes our comparison. We've seen something like this in our signal gen systems. Which is called the Laplace transform, right? So it's related to the moment generating function is closely related to the Laplace transform of the what? PDF of random variable. However, the difference is that we don't have a negative sign here, but that doesn't much matter, right? Because we just need to flip it. One of the difference may be whenever we talk about Laplace transform, usually S is a complex number, not restricted to real. That's why some people, when they define the moment generating function, they prefer using nu as a complex number. They want to make everything simple. But usually, when people talk about moment generating function, they assume nu is real. So we also take that point of view. Okay. And one of our lessons from signal systems is that given a function, the Laplace transform does not always converge because it's an integral for every complex number s. Similarly, this one may not exist, right? May not exist. So be careful. In our signal systems, we talked about reason of convergence, right? Which means that that integral may not converge. That integral may converge only in some specific small region. It could be very big, but anyway. Then why this is called the moment generating function? So the idea is this one. We differentiate the moment generating function and let's see what happens. So first order derivative. Of course, we differentiate with respect to nu because nu is the only variable. And let's assume that the order between integral and differentiation can be changed. Then what happens? Our new integrand becomes nu times, x times, because with respect to nu, we have x times e to the nu x fx dx. And what? Now, after differentiation, take nu equals 0. What happens? This second factor becomes 1. Then it's integral x density x dx, which is expected value of x. So what we do is that we take nu equals 0 to have the first order moment. So the moment generating function, if we compute the first order derivative and evaluate at nu equals 0, then we get the mean. If is very important, if it exists. Okay. We can do the same thing for the second order, third order, and the nth order moments. Very similar procedure we have. So you do it yourself. Got it? Now let me move on to the inequalities related with moments and moment generating functions. Okay, question. Yeah, that's a good question. So what is the moment? I believe that is, I'm not sure. I need to probably Google it or GPT it, or I don't know. But what I first faced the term moment, it was from my physics course. So we usually say that the rotational moment, right? And that is also related to momentum. So movement, resistance to move, resistance to something motion. So I believe the formula is almost the same as we learned in physics. For example, what is the rotational moment or rotational inertia over distributed mass of point masses? The rotational moments of distributed point system of point masses or distributed masses. That involves what? Integration of the distance squared times dm. You remember that? Yeah. So find the rotational moments and you see the same thing. So I personally believe that motivated the term moment. Okay, so moment generating function. Good question. Okay, let me move on to the inequalities. We are going to learn 3 inequalities. the Markov inequality, the Chebychev inequality, sometimes this starts with T and Chebychev, I don't know, but let me just use Chebychev, and Chernoff inequality. And by the way, Jensen's inequality is a little bit different from these three, so I'm not going to talk about it, but it's very, very important in information theory and communications and almost everything. First thing, what is the Markov inequality? What is the most important assumption? The assumption is that the mean exists, okay? And then you talk about the Markov inequality. Second, when do you use Chebychev inequality? Usually when the mean exists and the variance exists, okay? So as I put the numbers specifically, the Markov inequality is related to the first order moment. The Chebychev inequality is related to the second order moments. Usually if we say second order moments, it's like up to second order moments. So first order and second order. And why do I say n here for the Chebychev? Because as you see that in the bound, Markov inequality involves the first order moment, Chebychev inequality involves the second order moments and first order moment. The Chebychev inequality involves the moment generating function that can generate if it exists the any nth order moment. Got it? And these are differences of these three inequalities. What are the commonalities of these three inequalities? The commonalities are, of course, they can be put into a different form. You can talk about tail probabilities or sometimes tail end probabilities. What does that mean? It's like if you have a Gaussian, you have two tails here and there, but usually this part is called right tail and this part is called left tail. However, let's talk about right tail. One of the reasons is this one. What is the most important functions among these three? PDF, PMF, CDF. CDF, because from CDF you can derive the other two. So what's the definition of CDF? Probability of event that capital X is less than or equal to some value X. What about the other part? That is right and tail or right tail. Okay, so I'm saying that they are all about right tail, or you may say that complementary CDF. See that? This is simply 1 minus probability of X less than or equal to X, and which is 1 minus CDF of X. And also, this can be put into a similar form by defining this as, for example, Y, okay? Then it is simply, we can, of course, we can replace this. We can have a version of Chebychev inequality without equality. So let me just do it. Okay, so we remove this one, and then it's also related to the probability of X minus X bar less than or equal to K sigma, and which is 1 minus Fy of K sigma, something like that, okay? And also, you can have the CDF version of Chernoff inequality, so something like that. Here, I'm not sure which is correct, but just to try to derive two inequality sets. First one is that anyway, you consider tail probability, but without inequality. Then you have three inequalities, and also put equalities. They have very subtle difference, okay? When you talk about the condition on the equalities. Sometimes if you remove that, you also have to remove that. I'm not sure. You do it, okay? I forgot it. Okay? Anyway, so the commonality of these three is that they are all related to the right tail probability. And see that, what are the other commonalities? They talk about right tail probabilities are upper bounded by some quantity. Right tail probability is upper bounded some quantity. Right tail probability is upper bounded by some quantity. This important notification, realization, is not well often done by at your level of graduate students, but I really want to emphasize that, okay? So what are the commonalities? If some people ask you, you say, oh, they are all about right tail or tail end probabilities, and they also provide upper bounds. Then, for example, your professor or your interviewer may be shocked and will respect you if he or she also knows that. I believe most of your interviewers never realize this. They just probably remember, okay, there were some inequalities I never used and only appeared in the exams. What's the use of it? Never do that, okay? They are all upper bounds, the tail probabilities. And see that something interesting. The first thing is that, first, the Markov inequality applies to non-negative random variable. So it's x is greater than or equal to 0 almost surely. In that case, you have this interesting result. The tail probability is upper bounded by this value x scaled by mean. So what does that mean? Let's draw right side. Right side is something like this as a function of x. It's mu of x divided by x, right? So what you say is that your complementary CDF, there must be a decreasing function. CDF is an increasing function. CCDF, complementary CDF, must be a monotonically decreasing function. As far as you know the mean, you can find a very rough upper bound on the CCDF. That's amazing. So as far as you have two random variables having the same mean values, and if they are both non-negative random variables, you have a single upper bound. Very good. Not always, sometimes. And Chebychev inequality assumes something more, not only the mean, but also the standard deviation or variance. Then you can find a tighter upper bound. Now let's see, what about this one? Even though it has k, let's replace this as x. Then what is this? It's related to 1 over x squared, right? If this is called x, 1 over x squared. So actually, the Chebychev inequality is related to what? The bounding the CCDF by using something divided by x squared. Sorry, y squared, okay? Some constant. So as you know that the 1 over y squared is much faster decaying than 1 over x. Got it? Now, what about the Chernoff inequality? Chernoff inequality is what? It's related to exponential bounding. Be careful. Now, what is the variable? Variable is a, right? So given nu, some value of nu, what is this one? E to the negative nu a times m sub x of nu. So you have exponentially decaying bound on your complementary CDF. That's the implication of the Chernoff inequality. So what I want to emphasize is this one. I also remember at your age, I just studied very hard, tried to memorize and solve problems only. But as you are now a graduate student, try to verbalize of your results. By the way, this is practiced by your friends in your elementary school students, middle school students, high school, even undergraduates who underperformed you. They usually memorize equations verbally. They try to understand, but they usually never solve problems. But you are opposite. You just memorize because your brain was very smart. You could just photo memorize the thing and solve almost every problem, and you are here. But adopt your friend's approach too, because you require both of the tricks. So not only just, okay, something, try to verbalize. In Korean, 말로 바꿔라. Okay? So the Chernoff inequality is about the right tail probability upper bounded by an exponential function. That is your verbalization of the Markov inequality. About the proofs of these three, usually most of the even undergraduate books have them. 100% of graduate level books have them, and even my handout has that. However, interpretation, this type of interpretation rarely appears in the undergraduate and even graduate textbooks. So try to understand it this way. Okay, what about this characteristic function? This is very interesting. So given a random variable x, we've defined a moment generating function. And here goes another thing. This was related to the Laplace transform. And you want to use what? Something inferior, Fourier transform. And there are many notations, but I prefer this phi type notation. So I use this notation, phi sub x of omega. Okay, here omega in Fourier transform is real. So here omega is also real. And it's defined as expected value of e to the j omega x. By the way, I prefer using j instead of I to denote the square root of -1, but it's up to you. Some mathematicians, engineers love to use I. Anyway, so what's the difference between the Laplace transform and Fourier transform? In this case, you may say that, okay, if we restrict nu and omega to real, it seems that this is real times real in the exponent, and this is pure imaginary times real. It seems no difference. Interesting thing is this one. This may not exist for some random variable, but this function always exists. And you may wonder, okay, when I was an undergraduate student, I heard that the sum signal does not have the Fourier transform. But see the definition, and you will find the interesting thing. What is this one? E to the j omega x, density of x dx. And this is absolutely integrable, and its integral equals 1. See that? Absolute integrability of a function guarantees the existence of Fourier transform. So density function is always non-negative. So taking the absolute value of it doesn't matter. And also, if you integrate them, it's always 1 by definition of probability. So surprisingly, characteristic function becomes more fundamental in probability theory. The Fourier transform is more fundamental than Laplace transform, surprisingly. Okay, of course, the Laplace transform limited usually to real. Okay, because you say that, okay, let me replace nu with j omega. They are the same. Okay, so that's why I say that when people define the moment generating function, they say nu is real. Okay. Otherwise, what's the difference between Laplace, so moment generating function and characteristic function? Anyway, so characteristic function always exists and its derivative. And so the derivative also generates moments if it exists. Here goes something strange. The characteristic function exists. However, nth order derivative may not exist if the nth order moment does not exist. This is very strange. But anyway, there are many examples. So try to Google the Cauchy distribution. You will see that they have a table in Wikipedia. They have the closed form characteristic function. And if you differentiate that, you will find even the first order derivative does not exist. Okay? Because Cauchy distribution does not have the mean value. Anyway, so function itself always exists. It's a kind of Fourier transform or inverse transform of the PDF that is absolutely integrable. That is very important. And it fully characterizes the distribution. What does that mean? From the characteristic function, you can find the CDF. From CDF, you can find the characteristic function. And you may say that, wait a minute, where is CDF? Actually, you must use what? dCDF here for the precise definition using Stieltjes integral, not this just Riemann or Lebesgue integral. Okay, now we move to the second part of chapter. We have 3 minutes. So here goes the transformation, which is also, we also got a glance when we talked about the fundamental theorem of expectation. At that time, we had a deterministic mapping rule, which was simply a function. Now, our textbook names as T, but let me still use G, okay? So here goes X, and we have Y as the output. So X goes in, we have Y output. This is what? This is a transformation of the random variable X. Now, what would be our question? The first question is, as I already asked you, what is the output? Output is a random variable. That was our undergraduate level answer. Now, let me ask you, why? Can you answer that question more measure theoretically? Whenever I talk about measure theoretically, you replace this random number generator marked X into what? 2 blocks. First one, you have an underlying probability space. And what? Here, you have a measurable function of S, right? Now, what do we have? We just have a function G attached here, right?
Dr. Joe, it is time.
And as we've already seen, what is this? This is G composition X of S, right? This is a composite function, simply. And sometimes, of course, composite function may not be measurable, so we put an assumption that G is also measurable function. So here goes our assumption. G is measurable. Then if you take the measure theory course, this composition of G and X is a measurable function. Measurable function of sample is what? A random variable. So it's obvious. This entire block becomes what? Can be named as a random variable generator. Okay? So it's random variable. This is random variable. This is a function from S to R. Done. Okay? So as I told you, this measure theoretic approach with little knowledge, almost no knowledge, okay, gives you a lot of power to clearly understand what was vague before. Okay? Anyway, so first thing is that the output is a random variable because our composition of the random variable and the measurable function is a measurable function which is a random variable. Okay? Now, we investigate on what happens to the output by classifying our function into several things. The first is that when G is an affine function. So G is what? Simply A times input plus B. This is called affine function of the input X, right? And of course, when A equals 0, it's too simple. Output is always B. So we have even the density function of Y, very simply. Second, when A is positive. Third, when A is negative. And we can suddenly combine these two like this. Output equals absolute value of A in the denominator. And we have what? See that the density function of X must have the argument in X unit. So here, what? Y equals AX plus B. So X equals Y minus B divided by A goes in here. So we can very simply find the output PDF. Got it? Very simple. But how this is true? In order to show this, actually, you use the CDF. Okay. So first, try to find the CDF of the output, and then apply the derivative to get the PDF. Or here goes the more intuitive one. As I told you, the PDF is very, very appealing to our intuition. How? As you've seen, we generate a lot of dots in our scatter plot. And then we reduce the size by generating many realizations, and we have some PDF type thing. Actually, you can apply this by drawing Y equals AX plus B. And here goes the input, here goes the output, and you can understand that. Anyway, I'm going to stop here. And unfortunately, one of the problem involves this transformation of a random variable. And as you already have taken, I believe, undergraduate course, you can solve it. So I'm sorry that the quiz problem has one problem that is related to the transformation of random variables. So do not stop here. Study further on chapter 3. And then, yeah, I will cover the later part next week. Okay, good luck in your quiz.